start recording. So today we are happy to have with us YANNAI GONCZAROWSKI from Microsoft Research. So now he's doing his postdoctorate fellowship in Microsoft. Before that, YANNAI was a postdoctorate fellow here in Tel Aviv. He works mainly on the interface between computation, economic theory, game theory. And today I thought of Star Trek when I saw your title, To Infinity and Beyond. So the stage is yours, YANNAI.
Thanks. So actually, whether you think of Star Trek or Toy Story tells something about your age / the age of your kids, but we'll get to that. So To Infinity and Beyond, Scaling Economic Theories via Logical Compactness, or Why It Paid Off to Listen, Mathematical Logic 101. So this is joint work with Scott Commoners from Harvard, who's here, and Ran Shorer from Penn State, who should be here but may have been woken in the middle of the night by his kids as well. Let's start. So finiteness assumptions are baked into many game theory results. We have results that require finitely many sets of agents. We have results that require finite time horizon, future, or even more so with finite past horizon for sometimes zero to exist. We have results that require finite data sets, for example, in revealed preference theory. And usually this finiteness plays a real role in the analysis. And dropping finiteness, if we manage to do so, usually translates into either completely rewriting the finite case proof with more details, so we have no black box reductions that say, due to this fancy theorem, whatever was true for finite is true for infinite. Or sometimes it involves a completely new proof technique, more elaborate, that seems to have nothing to do with the finite proof, with the finite case proof. And generalizing each result, even if we already have it for finite sets, and even in the case that we have to rewrite it with added detail rather than reinvent the wheel, requires specialized tools. So for finite markets, for example, Nash equilibrium, we prove via Brouwer's theorem. For infinite markets, Peleg proved it via Schauder's theorem. And at this seminar, it's a bit harder because in other seminars, they usually ask people to raise their hand if they heard of Schauder's theorem, and then no one does that, but this is not the right audience for this. But you do agree that Schauder's theorem is more niche than Brouwer's theorem. And existence of a stable matching in finite markets, it's proven by an explicit algorithm, deferred acceptance, that we all know and love. In infinite markets, you need to venture to Tarski's theorem. Once again, I know that there are people here who think that Tarski's theorem is more natural than the algorithm of Gill and Shapley, but you're not the main people who do matching. But anyway, as you can see, even to generalize, even if the proof generalizes more or less without a lot of problem, we still need the specialized tool.
Are interruptions allowed?
From you always.
Anyway, whether they're allowed or not.
So Israel, you're the only one for whom I can't tell if the leaves around you are a virtual background or you're still hiking as usual.
Sure, I'm out on a hike right now. Yeah, I just stopped in order to listen to this seminar. But
I appreciate it.
In the middle of the jungle.
Yeah.
Why would you want, I mean, maybe I'm not the right guy to ask this, but why would you want to do a stable matching in an infinite market?
Okay, wait one slide, please.
Okay, fine.
But fair enough question. Okay. So today...
I won't tell anybody that you planted it.
We're going to get to it in exactly one slide, I promise. Okay. So today we're going to have a principled, widely applicable, meaning that we're going to do a lot of things using exactly the same approach. User-friendly approach, that's more fuzzy, but it's really going to be easier to reason like this. For lifting finite model results as black boxes without even knowing what the proof for the finite case is into infinite models. So one slide, this answers Israel's question. I wrote here one slide, if I may, for everyone except the seminar's audience. But thank you, Israel, for asking that question anyway. So here's a question. In practice, everything is finite. If we already have a finite model result, isn't infinity abstract nonsense? That's a question I usually get from computer scientists, but it's a fair question. I mean, why would you want infinite sets of agents? Why would you want infinite time horizons? When does time really start at minus infinity or end at plus? I mean, even forget end at plus infinity. When does it start at minus infinity? When would you ever be given infinite data sets as input? And the answer is, it helps even if you're interested only in the finite case. Results that hold for infinitely many agents are inherently somehow more robust. They're many times less susceptible to added friction, and that's also the case for stable matching, Israel. We'll get to that. And for generalizing results to hold for infinite past horizons helps us distill the existence of dynamic steady states. And for infinite data, it's true that you're never going to be given infinite data, but if you can think about whether you can deduce something about an agent's behavior from finite data or not in a revealed preference kind of way, and you know that you cannot deduce or rule out something given finite data, is that because the data is finite and you could have deduced or ruled out something given infinite data? Or is that because of an inherent limitation of the nature of your observations that even having infinite data would not have helped with? That's a question that we cannot answer without reasoning about infinite data, and that's an important question even if you don't really ever get given infinite data. And we'll get another example for why infinite data is needed later on. And so even if we only care about real life, knowing whether things hold for infinity it helps us better understand, get better intuition for finite domains. So let's talk about we're going to prove a lot of things today. So let's focus on a few settings that we all know and love. So infinitely many agents, we're going to talk about stable matchings, we're going to talk about Walrasian equilibrium and in trading networks. Infinite past horizon, we're going to talk about dynamic stable matchings with tenure. And infinite observed data, we're going to talk about revealed preference theory, of course. There are very classic results here that we all know and love. For finite markets, a stable matching exists, Gill and Shapley. In Walrasian equilibrium trading networks, a fairly new result from JTE, Hatfield et al. Gives us a Walrasian equilibrium on finite networks if preferences are substitutable. There's also work on dynamic stable matchings with a finite start and infinite future horizon. I'm going to introduce this model soon. You probably some of you don't know that. And rationalizability of finite demand data sets if and only if they satisfy GARP. Apriat 67 is probably the result that needs least introduction out of all of these. And in some of these, we already have results for infinite markets. So Elon, if you were a bit younger or your kids were a bit younger or older, depending on if you want to shoot for the first or third movie, Infinity and Beyond would have made you think of Toy Story, which is on the top right now. So for stable matchings, Tamás Fleiner proved in 2003 via beautiful argument that stable matchings exist also in infinite markets. There's a beautiful paper by Phil Rennie from Econometrica 2015 that, by the way, can you also see my cursor or only my screen?
The cursor is visible.
Visible, yeah. We see the cursor.
You see the cursor. Perfect. Thank you. So Phil Rennie, Econometrica 2015 showed that rationalizability of demand data sets, if and only if they satisfy GARP, goes on into even infinite data sets, although what you can assume, what you can or cannot rule out regarding the structure of the utility function is a bit weaker. We'll talk about that. So both of these are beautiful results. The first is proven via Tarski's theorem. Second one is proven via a new, completely different elaborate proof. So they're not generalized in the same way. And we also have many open questions. So we know that a stable matching, even a min-optimal stable matching, exists in an infinite matching market. Is the min-optimal stable mechanism strategy proof? We don't know. It's actually an open question that's been formally stated as an open question. And the challenge here is that usually in matching markets, we prove strategy proofness by appealing to the lone wolf theorem. That's a one-to-one version of the rural hospitals theorem. Maybe some of you have heard about it. It says that if you're unmatched in one stable matching, you're going to be unmatched in all stable matchings. And this is known. It was proved by Ravi Jagadistan that this does not hold for infinite markets. So if we have any hope of proving strategy proofness for infinite markets, we're going to have a whole new approach of proving it, not via the lone wolf theorem that does not hold for infinite markets anymore. Can we lift variant existence results? So there are matching results that are not deferred acceptance based, but they seem very close to the original model of the Galen chapter. If you're talking about matching with couples, for example, we'll talk about that soon. They're not deferred acceptance based, so a generalization via Tarski's theorem is very unlikely. Can we handle these? How do we handle these? It's very frustrating to reinvent the wheel for every one of these questions. For Walrasian equilibria, is there any way to prove existence in infinite networks? So the finite network proof is very delicate. It's very complex as it is. It seems very laborious to even try to extend it to infinite networks. And just to drive the point home that this is not me looking at someone else's proof and saying, I don't understand their intuition, so I can't generalize it. Actually, Scott Commoners is a co-author on that paper and on this paper as well. And he will certify to you that it's a proof that's so delicate that even the authors of that paper would not want to think about how to start generalizing it into infinite domains. And that's not to say that Scott or any of them is not brilliant, of course. So for dynamic stable matchings with the infinite path horizon, before I give you the open question here, let's talk about the model, for example, for a minute. So we have a set of women W and a set of men M. I'm doing it for men and women because that's the usual way to talk about one-to-one matching. I don't mean anything social or gender or anything about it. So please don't take it that way. So we have a strict preference for each participant over the opposing side, and we're going to have the women. You can think about the women as the schools; they always exist, and the men, you can think about them as the teachers. They come and go. They go into the market at some point. They retire at some point. So each man is on the market at a set of integer times, starting at the arrival of M and ending at the departure of M. And the matching chronology maps women time pairs to men who are on the market at that time. So each woman at a specific time can be matched to a man who is on the market at that time. And each man is matched at most once. And each woman time pair is matched at most once. And a match chronology is stable subject to tenure. So the idea here that connects the different times is tenure. Basically, once a man is matched, they cannot be demoted. They can only be rematched to a woman they strictly prefer. So tenure means that every man who is on the market at T and a T+1 weakly prefers his T+1 match to his T match. And stable means that a blocking pair may only exist at time T if it exists because the woman of that blocking pair retained her match from the previous round. So when the set of times is the natural, it's Games paper by Pereira, 2013. Existence is pretty straightforward. You solve for time T, you don't have any tenure constraints, you just run deferred acceptance. Then you inductively solve for T+1 by running deferred acceptance, but treating the T matches, the matches from the previous time of women to be their top choices in the current time. And that way you know that women will never throw out men they were matched with unless men propose to women they actually prefer. But that crucially depends on being able to start our induction at t equals 0, where we have no tenure constraints. What about
Please give the intuition for how the stability is formulated. I'm just a bit confused about that.
Sorry, say again?
Can you please give the intuition about the formulation of stability?
So you mean the definition of stability, or why this induction gives a stable matching?
The definition. So you define tenure simply in the sense that no woman gets worse off.
A man cannot cannot strictly prefer his previous match to his current match until he leaves the market. So he can only improve his matches from the time he arrives and until he departs. He could be unmatched in all of these times, but once he's matched, at t plus 1, he will be either matched to the same woman or to a woman he slightly prefers. This comes from
tenure, the tenure approach.
Tenure, yeah. It basically means that a teacher can only be kicked out of one school. He can only be removed from one school if they're moved to a school they prefer.
Yes, and my question is about the stability.
Okay, so stability means that at any time t, you cannot have a blocking pair MW. Blocking pair means that woman and man will prefer each other to the people they were matched with, unless, and this is the new thing, unless the woman out of that blocking pair is matched at that time to the same man she was matched with in the previous time. So it's possible that she may want a man and a man may want her back, but that does not materialize because she is stuck with the man she was matched to in the previous step because of tenure. You need to demand that, otherwise you're going to have inexistence. Okay, I'm going to move forward. We can go back to that later. It's not the most important example in this paper. But the point is, it's something that's very, if you believe me that this induction solves it, then it's something that's very easy to solve when you have an induction base, when you can start from t equals 0. It's very unclear what you would do if you had an infinite pass horizons. If the times were of the integers, so you don't have a minus infinity time, but you have a minus any number as big as you want time. So there is no start time, and there are men arriving and departing at the market at as early as you wish times. You know, there's no minimum time of a man arriving at the market or departing at the market. So you cannot, so you cannot start. There is no time where you can start at that time and say, we have no binding tenure constraints from previous times, so we can just run deferred acceptance here and start, like you could have done if time started at 0. And the annoying thing about stability here is that you cannot solve backward from any time. You cannot just pick a time, say, let's fix something here, or write deferred acceptance here, and start solving backward, because you may get stuck. So how do you do this? How do you do induction when you have no induction base? And I should also point out that there is here, I can give you an example when there's no single min optimal stable matching chronology. There could be 2 matching chronologies, and they would be incomparable. Half of the men, or countably many of the men would prefer this one, and countably many of the men would prefer this one, so go figure. So a Gale-Shapley deferred acceptance style proof, like in some variant of what we know, is quite unlikely here because of that, because usually deferred acceptance gives you a man-optimal solution. Okay, so let's talk about, so we spoke about rationalizability and GARP, but there are other theorems in revealed preference theory. What about other rationalizability result? There's for example, McFadden and Richter, 1971, rationalizability of stochastic choice. There are other examples as well in revealed preference theory. And specifically for McFadden and Richter's result, it's the most celebrated and oldest one, most well-known one we could find. The problem is that there are actually generalizations of this theory for infinite data sets, but they either add structural assumptions or weaken the definition of rationalizability to carry things over to infinite data sets. And we're going to ask, can you do such a generalization without adding structural assumptions and without weakening the goal of rationalizability? So basically today our goal will be to go over all of these, and for me to convince you that you can do all of these using the same approach and not even care how the original proofs were written, and actually not need a lot of math to do this. So our protagonist for today is going to be the compactness theorem of propositional logic, what's called logical compactness. And I know that many people here are familiar with it, but let me still give one slide crash course on what we're going to need, which is not a lot. So the idea is, how do you work with logical compactness? You start by defining a set of Boolean variables. These are going to be problem dependent. For example, if I can say, okay, if I have a set X that I care about, I can define some variable called GT. We're going to give this meaning soon for every pair of elements in the S set. That's fine. And then the set of well-formed propositional formulae is defined inductively. Formula is a fancy word of a way of saying formulas. I probably don't need to say this in a European seminar, but just in case, I'm used to telling this to Americans. Oh, I'm recorded. Delete that part of the recording later, Elon, please. So what are our set of well-formed formulae? So all atomic formulae. So each variable we defined is a formula. The negation of any formula is also a formula, and also the conjunction, disjunction, implyment, and mutual implyment for every two formulas is a formula. So for example, if GTAB is a formula for every NB, then the disjunction of GTAB and GTBA is also a formula. The negation of their conjunction is a formula, and also saying GTAB and GTBC implies GTAC. You by now understand what GT means, but we'll get to that in a second, is also a formula. And note, and this is going to be very important, formulas are always finite. By the way, but this is inductively defined. You cannot have an infinite disjunction, and this is going to give us a lot of pain, because things are just not going to be true if you try to use this for infinite formulas. And we're going to have this picture of my son Eshed playing very carefully with his big brother's Buzz Lightyear, the character that says to infinity and beyond in the Toy Story movies, whenever we're going to have to be careful about finiteness of formulas. So just to make sure that we handle formulas as gently as he handles Buzz Lightyear. Buzz Lightyear was not harmed during the making of this photo. Okay, so let's continue. So a model is a mapping. A model is a mapping from variables, these guys, the GTAB guys, to Boolean values. And the truth value of a formula in the model is defined inductively. So a model basically tells us which of the atomic formulas hold. And then if one holds and the other doesn't hold, their disjunction hold, but their conjunction doesn't hold. And if something holds, then its negation doesn't hold, and vice versa. You get the point. And the compactness theorem says as follows. So say that we have a set of formulas. Think about an infinite set. If it is satisfiable, if there is the model for which all of the formulas are true, then obviously every subset is also satisfiable using the same model. That's easy. That's not interesting. The interesting part is the converse. Compactness theorem tells us that if every finite subset is satisfiable, then the whole set of formula, even if it's infinite, large cardinality, whatever, is satisfiable. And that's quite remarkable. And to drive this point home, let's test drive this by giving a 3-line proof to Spielreing's extension theorem. So there's actually an extension theorem that's usually in the beginning of graduate econ textbooks. And a lot of times in textbooks we looked at, they either say the proof is beyond the scope of this book, or it requires advanced math, or they defer to a later chapter, or they prove it using Zorn's lemma. Whomever here tried to teach something, prove something to a class of economists using Zorn's lemma and everyone understood? Raise your hands if you did. Perfect. Okay, good. So let's reprove this very shortly using logical compactness. So let's define, okay, so you give me x, x may be infinite, you give me a partial order on x, I have to show you that a total order exists. Let's create a set of formulas because that's what we need for the compactness theorem. So let's start by, for every a, b, and c, adding these green guys. We have a hand raise from Jeffrey. Okay, so I'm not monitoring the chat. Elon, could I ask you, or Scott, could I ask you to monitor the chat and tell me if anything's going on there?
I've been monitoring. So far, it's mostly questions about spelling Tarski.
Oh, sorry about that. Thank you. But I think I spelled it with an I, right? Did I add it? Okay, I'll take a look at that later. Okay. Sorry. Okay, so let's start by adding for every a, b, and c, formula that says a cannot be greater than b. Sorry, either a is greater than b or b is greater than a. It is not possible that both hold. GT is going to signify a strict relation here. And if a is greater than b and b is greater than c, then a is greater than c. Perfect. And then let's also add this blue guy here for any constraint that we already have from the partial order. So you gave me a set X with a partial order. If that partial order says that some A is greater than some B, let's throw this formula in as well. So these formula, we're going to have infinitely many of these, but each of these is finite, regarding to what I said about each formula having to be finite. If we can prove that there is some model that satisfies all of these, that's a total order on X. That is consistent with the partial order that you've given me. How do I do that? Use compactness. It's enough for me to show you that every subset of these formulas, every finite subset of these formulas is satisfiable. Give me a finite subset. It references only finitely many elements. We have the induced partial order on that finite set. And the fact that for a finite set we can extend a partial order to a total order is completely trivial and well known. You can do it by induction. Each time pick an element where there's no other element that's big than it, make it the top one, continue, or whatever. That's it. End of proof of spline theorem. This product does not contain traces of Zorn's lemma. And let's do another warm-up that's more relevant to us. Let's prove that a stable matching exists in an infinite market using logical compactness. Once again, this is going to be a half-slide proof like most of the proofs you're going to see in this talk. So we're going to have just a model, an infinite set of women W, infinite set of men M. Each of them specifies their nth choice for every n. So each man, each woman says who their first choice, second choice, third choice, etc., etc. They could have, that could be infinite, that's fine. A matching is blocked by a pair MW. If this is vanilla stable matching, if M prefers W to his match and W prefers M to her match, stable if unblocked. Note that this is not a continuum model like many other models of infinite matching. There are infinitely many non-negligible players. This is a model where even though there are infinitely many agents, the effect of a single agent does not become negligible because of the size of the market. So it's very much closer to a finite model in the sense that proofs here immediately generalize the finite model. It's not a different model. So Gale and Shapley gave a proof that a stable matching always exists in finite markets. Let's prove it's only going to be this shaded box here. This is going to be the entire proof that an infinite matching exists that a stable matching exists in an infinite market as well. So we're going to have, let's define a set of formulas. For each M and W, we're going to have match WM. This is going to mean later whether W and M are matched or not. This is a Boolean variable. This is going to be the atomic formulas. So let's start adding formulas into our set of formulas. If M is matched with W, we don't want M to be matched with any other W prime. Let's add this for every MW and W prime. If M is matched with W, no other M prime should be matched with W. Let's add this for every M prime and W. If M and W are not mutually ranked by each other, let's add not matched MW to make sure they don't get matched. Okay, so basically the first two bullets here define a one-to-one matching. The third bullet makes sure it's individually rational. And now we're left with stability. We're going to add a fourth bullet that says this matching has to be stable. So this is a bit delicate. So how do we read this? We have, for every M and W, we do the following. So we have M and W. Note that even though the preferences of M has an infinite preference list and W has an infinite preference list, if M ranks W, then M ranks only finitely many women above W. Because if M ranks W, it could be in the 5th place, it could be in the millionth place, it could be in the 1,000,007th place. But it's in some finite place, and then there are only 1,000,006 women M prefers to W. So let's call them W1 to WL. Similarly, if W ranks M, then there are only finitely many men W ranks above M. Let's call them M1 through MK. And then we're going to say, if M and W are not matched, then one of the following holds. Either M is matched with W1, or it's matched with W2, or it's matched with W3, etc. until WL, or W is matched with M1 or with M2, etc. until MK. So if they are not matched, they're not blocking because if one of them is matched to someone they prefer to the other. This is exactly stability. And that's more or less the end of the proof. Why? Because here is a set of formulas and models of this set correspond in a one-to-one way to stable matchings in the infinite market. We have to show that a stable matching exists, so it's enough to show that this has a model. How do we show that this has a model? Using logical compactness. It's enough for me to show that every finite subset of this has a model, but a finite subset only mentions finitely many men and women. A stable matching in the market, in the finite market of only these men and women, is going to satisfy all of these formulas. So every finite subset of the formulas is satisfiable. So the entire subset is satisfiable, and a model for the entire subset is a matching in the infinite market. We have to be a bit careful here. As I told you, W1, this formula is finite because there are only finitely many women that M prefers to W, finitely many men that W prefers to M. But that's fine, and we're done. And note that this was a reduction in the sense that I have used Gale and Shapley's theorem in a finite market. I do not care how it was proven. We lost a loan. Okay.
Why did you lose me?
Oh, I suddenly didn't see you anymore. I don't know. Okay.
I have a question for you.
Yeah.
Also run Smorodinsky had, which is you assume something about the order, the ranking of men and women. You assume that essentially order, right? You have.
Sorry.
You assume that men rank women according to a well order. There is a maximal women, a most preferred women, a second preferred.
Okay, good. Let me answer your question and then tell you the question that you really wanted to ask. Okay, I'm sorry. So the answer is, if it's not a well order, there need not be a stable matching. It's very easy to see that. Assume that it's not a well order. That means that there is some set of men. It means that there's some man and some set of women such that this man does not have a most preferred out of these women, right? Now have all of these women prefer this man at the top, have no other woman rank this man. Who is this man going to be matched with? You cannot form a stable matching. The question that you really wanted to ask is the following. YANNAI, you assume that the preferences of the men and the women are of order omega and not of another will order. Right? Because there are will orders that are not order omega. That's the question that you really wanted to answer. And the answer is yes, this proof is limited in that way. Okay, so we reproved the existence of a stable matching in an infinite market. Reproved because Tomasz Kleiner already gave such proof. And we actually the same thing, you do this more carefully, add some more stuff. I'm not going to do it right now. You can prove the existence of a optimal stable matching, which was still already known. It's kind of a second order result because it says we not only prove the existence of a stable matching, but we somehow can prove that one of them is better than all the rest, even though we non-constructively prove the existence of the rest. What about strategy proofness of the optimal stable mechanism? We don't have an algorithm for finding the optimal stable matching, but if there exists one, then you can define a mechanism. Given preferences, it outputs the optimal stable matching, whatever it is. In the finite case, we have strategy proofness of that mechanism due to Dubins and Friedman and independently to L. Roth. What about strategy proofness in an infinite market? The problem is that we don't have an algorithm whose execution we can trace to say, here incentives can or cannot be broken. What do? And note that this doesn't even look like an existence result. And logical compactness is good for existence results. This doesn't look, saying a mechanism is strategy proof doesn't look like an existence result. So if existence of the optimal stable matching was a second order result, this is at least a third order result, if not more. Nonetheless, we have a proof that's not much more complicated than the one in the previous slide. It fits in one slide as well. I'm not going to go over it now because we're a bit short on time, but I encourage you to take a look at the paper. This is a proof that's not, as I said, uses, and again, the nice thing is it uses strategy proofness in the finite market as a black box. We don't need to know how it was proven. You restrict to a more carefully chosen finite subset, not only the people mentioned in this formula. And as I've already noted, usually strategy proofness is proven using the lone wolf theorem. It fails in infinite markets. We obtain strategy proofness nonetheless. This actually shows us that the lone wolf theorem is more brittle than strategy proofness, which is the converse of the intuition of any matching theorist I've spoken to. So this actually helped us, going back to Israel's question of why do we care about infinite domains, this actually helped us gain intuition to the fact that strategy proofness is in fact more robust than the lone wolf theorem in matching markets, in contrast to folklore belief. So what about variance? We spoke about that. So in the US residency match program, couples and doctors are allowed to jointly submit, a list of hospitals. If there are two married doctors, they can submit a list of pairs of hospitals. And a blocking coalition could be a single doctor in a hospital, a couple in two hospitals, or a couple in a hospital. And even in simple many-to-one matching markets with responsive preferences, that's the easiest kind. There's a master preference list for each hospital, plus a capacity at which they're capped, so there are no weird complementarities or substitutes, but only only quota and a master preference list. Existence of a stable matching is not theoretically guaranteed. Nonetheless, there's a beautiful near feasibility result by Nguyen and Vohra from AER 2 years ago that says that in any finite many-to-one matching market with couples and capacity vector K, so K is the vector that says this school has 50 slots for residents, this hospital has 50 slots for residents, this has 2, this has 8, this has 80. there exists a capacity vector that's very close. Each quota of a single hospital is tweaked by at most 2, such that a stable matching exists with respect to this tweaked quota. That's a very beautiful theorem that says maybe you can't get a feasible matching for the original market, but you can tweak the quotas only a little bit and you can get stability. And it's a completely different proof than Gill and Shapley's. It uses Scarf's lemma in a beautiful way, doesn't use deferred acceptance. Tarski's theorem is unlikely to be applicable in this case to relaxed finiteness because Tarski's theorem that Tamasha's infinite proof for the existence of a stable matching really encodes deferred acceptance into a lattice operator. Logical compactness here, as we show, can help us. Even though the original proof is starkly different, we're going to have a proof that's virtually identical to our proof for generalizing vanilla matchings to infinite domains. And I can tell you this proof without you guys knowing how Nguyen and Vohra proved their near feasibility result, which is nice. So variables, we're going to have the same variables. Doctor, hospital, are they matched or not? We're going to have a new variable for each hospital saying capacity HK, meaning the capacity of H is K. And I'm going to say for each hospital, their capacity is between KH minus 2 and KH plus 2. This is a finite disjunction of 5 formulas. That's fine. And we're going to say that if the capacity of the hospital is something, it can't be something else. That's like if a woman is matched to a man, she's not matched to another man. And we're going to have the same formulas we already had, saying that if a hospital is matched to, if a doctor and a hospital are matched, that doctor is not matched to a different hospital. We're going to have a slightly tweaked version for the hospital, saying that if the capacity of a hospital is Q, then if it's matched to Q specific doctors, it cannot be matched to another doctor. That's just saying it's not matched to more than Q doctors. And so on and so forth. Every formula that you saw earlier, I'm going to say if that formula has a hospital in it, I'm going to say if the capacity of the hospital is Q, then, and then a version of that formula that's tweaked for capacity of Q. That's it. That's the only change from the proof you saw earlier. Any model of this is a stable match, is a near feasible up to quota changes of at most 2 in the original market. Take a subset of this set of formulas. It only mentions finitely many doctors in the hospitals. A stable matching there exists by Nguyen and Vohra, so that set is satisfiable. All of the finite subsets are satisfiable. The entire set is satisfiable. We have near feasible stable matchings even in infinite markets. And look, you can't really see, but there's nothing up my sleeve. I used nothing to do this. It's exactly the same proof as in the vanilla case, even though the proofs for the finite cases are starkly different. We don't need to reinvent the wheel again and again. So we've reproved this. This is new. We've proven this. We've proven this new. Let's talk about infinite past horizons. I already gave you the riddle. Yeah. Someone said something. Israel. Or maybe no. Okay. So I already gave you the riddle. I explained to you the model of matching with tenure. I asked you how can you solve this if you can't do induction from time 0 because there are earlier and earlier times. You use logical compactness. What do? You write an infinite set of formulas that's very different. You've all seen this, the vanilla case. You can now, each of you know enough to write an infinite set of formulas that says we have a stable matching chronology in this infinite past horizon market. Now give me a subset of that set of formulas. It only mentions finitely many times, so it mentions some earliest time. Use Pereira's induction to solve from that time onwards, so you can show that the finite set of formulas is satisfiable. Boom, logical compactness, the whole thing is satisfiable. There is a stable chronology even when there's no minimum start time. We just did induction without an induction base. There is some local finiteness condition that is needed. Eshed is here to remind us of that. I won't go through that now, but let me just say that if that local finiteness condition that was required for all our formulas to be finite fails, then we actually have a counterexample that shows that there is no stable matching chronology. So here, local finiteness is not something imposed on us by our specific way of proving, but rather it's something that helped us flush out a counterexample and actually turned out to be required. Great, so we did this. Walrasian equilibrium. Okay, so we're a bit short on time, so let me just tell you that if we want to find a Walrasian equilibrium or any kind, or Nash equilibrium, and any kind of equilibrium with prices or probabilities or anything that is on a continuum, the problem is that if you want to express continuous prices using it would require infinite formulae. Why? Because you can't say the price of this object is this price or this price or this price or this price or this price if it can take infinitely many different prices. So the crux of our argument here, and you can fill out the rest or read the rest because the rest isn't really very interesting, is to look at the epsilon equilibria. Every theorem that gives you an equilibrium in general prices or a Nash equilibrium in general probabilities will give you an epsilon equilibrium in prices on a fine enough grid, or an epsilon Walrasian equilibrium in prices on a fine enough grid, or an epsilon Nash equilibrium with probabilities that are finely enough discretized. Then you can say the price of O is either this or this or this or this in jumps of epsilon through the entire domain. Then you can write out equations that say we have an epsilon equilibrium in the infinite market. Then take a look at a subset. It only refers to a finite subset. You know that the epsilon equilibrium there is, you lift it using compactness to the infinite market, you get epsilon equilibria for arbitrary epsilon in the infinite market. That's it. Using standard limit arguments, you get normal equilibria in the infinite market. Sorry if I'm going for this a bit fast. I wanted to leave time for revealed preference theory, which is something we're really, really excited about.
YANNAI, very
So
quickly, before you move on to revealed preference, there are a bunch of questions about existence versus constructiveness.
Okay, so none of this is constructive. Can you summarize the questions for me, or do I open them?
Questions were versions of that.
Existence and infinite needs some measure and topology. That's if you talk about, so thanks Rita for the question. That's existent. Okay, so the answer is so some of the things that we did are for as I told you, they are for any cardinality, but in some of them we had some assumptions that basically said some things are enumerable, like what Alon asked about if any man lists their first woman, second woman, third woman, etc., then it means that they only list countably many women, even though there may be infinitely many women in the market. So for the Walrasian equilibrium, as I said, we're doing Walrasian equilibrium in trading networks. And in these networks, we assume that every person has at most countably many neighbors. Otherwise, there are many, many problems. The reason that we're doing that is not because we're scared of uncountability. You know who my advisors were, etc. That's not and you know also my co-authors. The thing is that we really wanted models that don't make people become negligible. We really wanted models that are very closely related to the finite markets, extend them, but are closely related to them in the sense that they generalize results from them, they give intuition for the finite results, and going to uncountable in the way that makes each agent negligible, and that indeed would require measurability and stuff like that, would have told us less. That's the go-to thing to do, right? That's where a lot of technique already is, but we feel that it would have taught us less about the finite markets from our perspective. Obviously, there are very beautiful papers that do this. We're not saying that that is not interesting, but we were interested specifically in in seeing what happens when individual players still have non-negligible influence.
YANNAI? YANNAI?
Yes, Ron.
So going back to Rita's question, to begin with, is our protagonist, is that an existing theorem to begin with? I mean, I'm as an ignorant about these things, or is there some construction in the proof of the protagonist theorem?
So the protagonist theorem, you can think about it as a watered down version of Tikhonov's theorem, which means that it's not really constructive. I say watered down because of three reasons. First of all, it's provably weaker than Tikhonov's theorem. Tikhonov is equivalent to choice. Compactness is a bit weaker than choice. Second of all, it's watered down. Well, obviously doesn't let you do everything that Tikhonov does. But the third, it's watered down in a good and bad way because it basically defines the topology for you. If you want to use Tikhonov's theorem, you have to start defining your open set and closed sets and things like that. And this is basically Tikhonov on the product space of binary metrics, of metric space that only have two elements in each of them. So it's restrictive, but on the other hand, it's so easy to use. But no, the proof is basically, it's non-constructive. The proof, you have to do either some kind of transfinite induction, or to do all these tricks of taking infinite unions of things, or Zorn's, you can, all of these are a bit overkills, but basically, I don't know of anything that could be called constructive as a proof of this. So that's one of the limitations of our technique, but as Israel mentioned, we don't really need to apply this in practice. We need to learn from this what is true and what is not true. But obviously, if you manage to reprove something we did here constructively, that would be amazing and we would be thrilled. Okay, so we have only 5 more minutes left, so let's talk about Afriyat and Rennie because we're very excited about that. So we have a data set. A data set is a subset of Rm plus minus the 0 vector. It represents observations. An observation in S, an observation P comma X, basically means that when a consumer, we're going to have the same consumer, one consumer, if they face prices P, if he or she faces prices P, then they choose the bundle X. And this has the inherent assumption that the budget is P times X. So they always maximize their budget. And the goal is to rationalize S via utility function. So basically we want to find a utility function such that given prices P, X really does maximize the utility of anything that's possible within budget given prices P. And we want to do this by a non-degenerate utility function because a constant utility function is cheating because it rationalizes everything. And Afriyat 67 tells us that we can rationalize S if and only if the observations satisfy GARP. Never mind what GARP is, that's the beauty of our proofs. We don't need to know what GARP is. And these imply, if, in this case, when it's rationalizable, if and if, i.e. when it satisfies GARP, this means that it's also rationalizable by you, that it's continuous, concave, non-decreasing, and strictly increases when all coordinates do. That's the non-degeneracy condition. So, and this is the big win of economists saying assuming concave utilities is without loss. What about infinite data sets? Why is our infinite data sets interesting? For 2 reasons. First of all, what if you're given the data set of all observations? Is it true that you cannot rule out concavity even then? Is it true that it's rationalizable if and only if GARP? Even then, even if you're hypothetically given all of the observations of the world, if data quality is not an issue, is this still, do the same things still happen? Second thing is, say that I gave you 1,000 demand points, and I asked you to predict what a reasonable completion of these demand points looks like. Now, if you make some kind of partial form assumption, you assume Cobb-Douglas utilities or whatever, that's easy. Say that you cannot make any functional form assumptions. Can you tell, if I want you to tell me what are all the possible completions, meaning over all infinite possible demands, like the whole demand function, what are all the reasonable completions of a finite set of demand observations? Your answer is going to be a set of demand functions. Each of them has an infinite domain, so you have to reason about infinite data domains. And really, Rennie gives us a way to do both of these. And is 10 really strict, Elon? You're muted. You're muted. You're muted.
Okay, so it is not strict, but it is better not to
abuse.
To let us continue with our afternoon.
Okay. Okay, so I will tell you. Okay, so I will tell you that Phil Rennie showed that even for infinite S, rationalizable if and only if GARP. So this holds, but quasi-concavity concavity becomes quasi-concavity. He does this via a new and elaborate proof. It's also known, I think it's Israel's example from the 70s, that you can't just assume continuity or concavity, that is with loss. And the point here is that strictly increasing when all coordinates do will make it a bit hard for us to do this proof, but we can nonetheless do it. That's the crux of this proof. I'll leave you to read that in the paper. And compactness gives us a concise alternative proof of the entire force of Rennie's theorem. Everything you see here, quasi-concavity, non-decreasing, everything, in a fraction of the pages. And as a bonus, it's really, really crisp where quasi-concavity comes from here. Maybe for Phil, it's also crisp from his proof. For my intuition, this solved that problem as well. And the answer is because quasi-concavity is ordinal and concavity is not ordinal, and particularly quasi-concavity is maintained by discretization. And I already told you that when we have infinitely many utilities or demand levels or probabilities or whatever, we need to discretize to use compactness. So, and concavity is not maintained by discretization, quasi-concavity is. And once again, this is something that seems to be arbitrary and forced on us by concavity, by using compactness, but it's already been shown that this is a necessary condition. So I will not walk you through the proof, sorry, but this is the entire proof, 2 slides, not 1, but that's it, done. I will skip stochastic choice, but I will also tell you that we were successful. Okay, so we reproved Rennie's result, and we were successful in our quest to generalize McFadden and Richter's result to an infinite domain without adding structural assumptions and without weakening rationalizability. So, as I promised, we can do everything using this one approach. Takeaway slide, last slide. Results for infinity teach us about the real world. Results that hold for infinitely many agents are more robust. They're many times less susceptible to added frictions. For example, strategy proofness, more fundamental, more robust, less susceptible to frictions than lone wolf. Generalizing results for infinite pass horizons helps us distill the existence of dynamic steady states. Theorizing about being given infinite data sets, such as observations of every possible agent's behavior, that's what we just talked about, helps us discern between reasons for the inability to deduce information. So data finiteness in Afria's theorem is the reason that we cannot deduce whether the utility function of the consumer is continuous or concave. We actually can rule that out if we have infinite data, but we cannot rule quasi-concavity out using infinite data. That's an inherent limitation of observing only demand. And logical compactness is a cross-domain, user-friendly approach for old and new results, as I've shown you. Lets us reason about finite models in regular language. We don't need limiting process. We don't need weird topological structures. We don't need convergence. It's pretty straightforward. I mean, there is an art to getting the formulas right, but you don't need any obscure theorems. You just need some creativity. You need to be careful, as I said, about not accidentally assuming that you can have infinite formulas. And we kind of hope / like to think about this as non-standard analysis, and we hope that maybe in a way that we're able to simplify many things in general equilibrium theory. Maybe logical compactness will find a lot of other uses in economics. We actually know how to do even more stuff than this. I only gave you the highlights. This slide is for Elon. Now you have to think about whether this was here to begin with or whether I managed to somehow ask someone to do this during this talk. Just for you, Elon. And thank you everyone for being here. If you have any more questions, I'll be happy to answer. Yeah, Piotr.
So about the kind of philosophical question about this whole exercise. So you said that we're interested in infinite models because they give us robustness for the finite models. But then in many of the results, you had to assume some sort of regularity, so to say. So for example, in the matching model, you had to assume that the preferences are well ordered. And so I'm not 100% convinced that when you assume regularity in the infinite model, that it really is a robustness exercise, because it just tells us that there is some infinite model that extends the finite model in which things still are true. But if it's not true for sort of all infinite versions of this model, then I'm not sure I would interpret this as robustness. So I'm not sure what is a well-defined question, but I am wondering about the motivation for the exercise.
Okay, so fair enough question. So I think that at least, I'm not a revealed preference person, so I cannot vouch for that holding for. So I mean, I assume actually for reproving Rennie and reproving McFadden and Richter, we made no such assumption whatsoever. But as a matching theorist, and Scott here is even a matching theorist for much longer than me, I think that I can just say that we didn't get your question from any other matching theorists, and we spoke to quite a few. So I think that for matching theorists, well order is a natural assumption to maintain, and is very natural even if you talk about extensions. So they still find value in our extension and our notion of this kind of robustness. I agree with you though that in other, making assumptions, that in some sense, one of the harder parts of economics, modeling and making assumptions and things like that. So I agree in general that you have to be careful if you need to inject assumptions to get this local finiteness condition. You need to be careful about that and make sure you don't, in Hebrew you say throw away the baby with the bathwater. I'm not sure if that's an expression in English, but it's specifically for matching. I'm familiar, and I've worked enough on matching. I worked with people who worked even more on matching. We spoke to a lot of matching people that I can fairly confidently say that a lot of matching people do not think that that is an issue specifically here. But the general point is of course valid. Soren does not require the set to be enumerable. That's right. But when we proved Spielrein's theorem way back here, we also did not assume any kind of enumerability. This 4-line reproof, the green and blue equations of Spielrein's theorem assumed nothing, had no traces of anything in it in terms of that kind of conditions or enumerability or finiteness or localness or whatever. This is actually X can be any set whatsoever. Give me any partial order whatsoever. We can extend it to a total order. So it's true that SORM does not require the set to be enumerable. Yeah, okay.
So if you,
I hope I answered that as well.
can I ask a question?
Yeah, sure. Hi, Rita. How are you?
Thanks. How are you?
Good, thanks. With 2 small kids at home in the US, daycares have not returned yet. So,
Some quick question. So if you take backward induction for zero-sum games, take just determinacy. You have one player choosing 0 or 1, the other player choosing 0 and 1. If it's finite, then you know that there is always, the game is determined. So Zermelo's theorem. Now imagine you take Gale Stewart, and it's infinite. Now you know that there are sets such that it's not determined. So how your results can apply to this extension from finite to infinite?
I cannot.
Why you cannot apply your result? Because it cannot be true. You should have to have this to have determinacy in infinite game. You should have, for example, the set that you want to. You should have some Borel structure, some Borel assumption on the set, you know.
So I'm not
Martin's theorem.
I'm not familiar enough with that to answer it off the top of my head. Scott, do you have any idea? Do you have a good answer to that? Scott nods his head. He's muted.
Shaking my head. I don't have an answer either. I'm sorry.
The answer. I mean, I guess the generic answer would be it would be interesting to look at that. If the infinite result is not true, then it means that either you can't formulate something as formulas, or the formulas turn out to be or the formulas turn out to be infinite in length for some reason, or maybe you can do this using finite formulas, but then when you have to show that a finite subset is satisfiable, maybe that finite subset does not correspond to a finite time game, like the nice correspondence in the cases that I showed you. I'm sorry.
A great question.
Yeah,
it's a great question. Well, we'll go and figure it out. That's a really
we'll go and
question.
figure it out. And actually,
I think the first proof of Gale Stewart is for A, which is open or closed, and here they come back to the finite world, let's say. But then there is this more deep proof of Martin that Elon is studying now, I think. And here I don't see how you can. So it could be interesting to look at, I think.
So Rita, could I ask you, because my memory gets erased after seminars, especially in the morning, could I ask you to email me your question, please?
I will do.
Thank you. Thank you so much.
Thanks. It's a great question.
Yeah.
Are there more questions?
Comments, flames?
Movie references.
Very nice.
Okay, if we reach the point of no more references, then that's a steady state of talks, which is we're happy with.
So many thanks, YANNAI, for this very nice presentation.
Okay, thank you all. I'm sorry I didn't get a chance to do. Actually, if anyone wants to stay, then I mean, I don't know if it's like, should we do that? I should probably not take up more of your time. Yeah. Okay. So thank you all. Thank you all very much for being here in the late afternoon / early morning, depending on where you are. Stay safe, everyone, and thanks again for coming.
Goodbye.
Thank you. Bye-bye.
Bye-bye.